In this example, we're taking the results of a chemical experiment and determining an empirical formula. Now, we've done something like this before. We look at the compound and see what it decomposed into. It decomposed into nitrogen and oxygen. That means that its chemical formula is N something O something. So we can represent that as NXOY, and we can write its decomposition reaction. NXOY decomposes into nitrogen, which is a homonuclear diatomic, so that's N2, and oxygen, which is also a homonuclear diatomic, so that's O2. To determine the coefficients of those products, we're going to have to determine how many moles of each product were made. All right, well, we know there were 2.34 grams of nitrogen made. To convert to moles, we look at the periodic chart and find that the mass of nitrogen atoms are 14.0. However, we have a nitrogen molecule as the product, N2. So its mass is 28.0 AMUs. That means 1 mole of N2 is 28.0 grams of N2. So now we can convert to moles. We take the number of grams, 2.34, and multiply by the conversion relationship with grams on the bottom, so that they cancel, and moles on the top. So in the end, the chemist made 0.0836 moles of N2. Now we do the same thing with O2. The entry for O on the periodic chart says that O atoms have a mass of 16.0. We're not dealing with oxygen atoms, however. We're dealing with oxygen molecules, O2. So we have to multiply that number by 2. So the mass of oxygen molecules are 32.0 atomic mass units. That means 1 mole of O2 has a mass of 32.0 grams. So that's our conversion relationship. We take the number of grams we have, 5.34, multiply by the conversion relationship with grams on the bottom and moles on the top. That way grams cancel and leave moles. And we find that the chemist produced 0.167 moles of O2. Now, these numbers aren't nearly as nice as what turned out in the last example, are they? In the last example, we made 1 mole of carbon and 2 moles of hydrogen. Here we're making 0.0836 moles of nitrogen and 0.167 moles of oxygen. Okay, those numbers aren't very nice, but we'll toss them into the chemical equation anyway. The chemical equation won't be realistic yet, but we'll do something about that in a minute. So the chemical equation is NXOY decomposes into 0.0836 moles of N2 and 0.167 moles of O2. Now what we need to do is turn these numbers into integers. How can I do that? Well, there's a trick that mathematicians employ every now and again. If they need to turn a group of numbers into integers, they divide by the smallest of them, and they see what happens. So let's take these two numbers, 0.0836 and 0.167, and divide by the smallest of them, 0.0836. When we do that, 0.0836 divided by 0.0836 is 1, and 0.167 divided by 0.0836 is 2. Now, in terms of significant figures, we have 3 significant figures, so it's 1.00 and 2.00. But at least now we've got integers, or something close to integers. Now, just like before, 1.00 doesn't mean much in a chemical equation because the numbers are supposed to be exact, so let's get rid of the .00s. Now I have a pretty simple chemical equation. NXOY makes N2 and 2O2. To balance this equation, X has to be 2 and Y has to be 4. All right, that's a chemical formula, but it's not an empirical formula. This kind of experiment can only determine the empirical formula of a compound. To determine the chemical formula, we need to know something else, like the mass of the chemical involved. We don't know that in this case, so the best we can do is an empirical formula. Remember what an empirical formula is. An empirical formula is a formula that contains only the simplest whole number ratio of atoms. This formula doesn't do that because 2 and 4 have a common factor, 2. So this isn't the simplest whole number ratio. To get the simplest whole number ratio, I need to divide by the common factor. Common factor is 2. So when I divide by 2, I get the true empirical formula, NO2. That's the answer to the question.